Hello, everybody. My name is Nikhil Shukla, and I'm an assistant professor at the University of Virginia. And I'd like to thank you for this opportunity to discuss some of my group's work on exploring novel hardware-centric approaches to solving computationally hard problems. So let's start by looking at what computationally hard problems are. It turns out that in computing, not all problems are created equal, and computers essentially find it more challenging to solve some problems over others. A very simple example of this would be, let's say, if we take multiplication versus addition, it turns out that a computer is going to require more steps or operations to execute multiplication than addition. Or in other words, multiplication is more challenging than addition. Now, of course, today's computers can handle multiplication and addition just fine, but it turns out that there is a larger class of problems where finding the solution can become intractable because the number of operations is so large that even state-of-the-art computers are unable to execute these problems successfully. So an elegant way to understand this idea is using complexity. Complexity essentially looks at the evolution of the number of operations as the input size increases. So, for example, in this graph shown here, if we look at the blue curve, we can understand that as the input size increases, there is a linear increase in the number of operations, or in other words, this specific problem would have a linear time complexity. Similarly, other problems might have logarithmic complexity as shown in red, or parabolic complexity as shown in black. But it turns out that there are certain problems which also have an exponential time complexity where the number of operations increase exponentially as the size of the input increases. And you can imagine that with such problems, by the time you get to problems which are large enough and of practical importance, the number of operations are so large that they essentially become intractable to solve, even with state-of-the-art computers that we have with us. And turns out that these type of problems are typically called as NP-hard problems. Of course, complexity is a topic that has been extensively investigated in theoretical computer science. This Euler diagram that you see in the inset, classifies these problems according to their various properties. So, for example, a problem which has polynomial time complexity denoted by P could be solved in polynomial time, but then there are other classes like NP, which is non-deterministic polynomial time, and then subcategories like NP complete and so on and so forth. But the bottom line being that NP hard problems are ones which have this exponential time complexity, and these are the ones that essentially become intractable to solve as the problem sizes increase. Now, one place where you can find a lot of these NP-hard problems is combinatorial optimization. Now, combinatorial optimization in the simplest sense is essentially the process of identifying the right combination under a given set of constraints or conditions in a discrete domain. So an easy way to represent combinatorial optimization problems is using graphs. So this graph on the left shown here essentially consists of nodes, which would be quantities, 1 through 6, and the edges between the nodes essentially represent the relationship between the quantities or the parameters. And so, for example, if this graph were to represent a social network, then the nodes 1 through 6 might represent people, and the edges might be used to represent whether the specific people know each other or not. And it turns out that computing properties of this graph or analyzing these graphs, some problems can be indeed NP-hard and computationally intensive. A few examples are shown on the right. So the first one is that of maximum clique, which is the objective here is to identify the largest set of nodes which have all-to-all connectivity within the graph. So, for example, here the nodes 1 3 6 would be a clique because all of the nodes are connected to each other, and it would not only be a clique, but it would be the maximum clique because you would not be able to find a set of nodes of larger size. So, in other words, four nodes which have this all-to-all connectivity property. Similarly, 2, 4, 5 would also be the maximum clique of the graph. Similarly, another problem example is that of maximum independent set, where the goal here is to identify the largest set of nodes which do not have an edge amongst themselves. So here, exactly opposite to the maximum clique, we try and identify the largest subset of nodes which do not have an edge. And so here the answer for that would be 4 and 6, 1 and 5, or 2 or 3. So these are three solutions to this problem. And then the last one is the maximum cut problem, which we will extensively use as an example problem throughout this talk. And the goal here is to divide the nodes of the graph into two sets, represented by the orange and the green, such that the number of common edges, or in other words, the number of edges that cross the red partition out there, is as large as possible. And so again, this is the maximum cut problem that finds that is a commonly used benchmark problem when it comes to solving combinatorial optimization. Now, of course, the problems that we looked at in the last slide were very small, but in reality, practical real-world networks have really large graphs, as shown by an example graph out here. And it turns out that solving for those properties in these real-world networks is where these problems become computationally intractable. And so the idea is that even though smaller graphs are easy to solve, there is an exponential increase in the complexity of the problem as the graph size increases. Now, of course, these two slides, we have only focused on the theoretical concepts of graphs, but it turns out that all of these concepts find extensive practical applications, ranging from social networks, community detection for defense, or VLSI design, where interconnect routing is done using or is performed as a combinatorial optimization problem, or train neural networks with interpretable classification rules. So a neural network that can explain its decisions would be a NP-hard problem, training the network. And then, of course, even problems in fault tolerance analysis for mission critical systems, it turns out to be a hard combinatorial optimization problem. And so the point that I want to emphasize here is that if we can figure out a way to accelerate these problems, there is the potential of real world impact. Now, of course, one of the important points that I'd like to emphasize about combinatorial optimization before we delve into the approach that we've explored is that essentially combinatorial optimization is equivalent to maximization or minimization of an objective function. So in other words, when we solve for a combinatorial optimization problem, we are essentially maximizing or minimizing a function. And of course, this function is in the discrete or the combinatorial domain. Now, to explain this idea, we will again go back to the maximum cut problem. And as I mentioned before, the idea is to divide the nodes of the graph into two sets such that the number of common edges, or the ones that cross that partition out there, is as large as possible. And so the way we can develop the objective function for this problem, which is actually specified at the bottom right, given by this H term out there, is by basically creating these two sets, and then we create a rule such that if a node is placed in, say, set 1, it's assigned a value of +1, and if the node is placed in set 2, it is assigned a value of -1. And of course, these values can be used interchangeably. Now, it turns out that that is the assignment for the nodes. And then for the edges, we essentially use the rule that if there is an edge between node I and node j, then the interaction term, which is jij, is equal to -1. And so negative jij would be +1, and then if there is an absence of edge, then the jij term would be 0. Now, if you actually work this problem out, you can essentially specify that if an edge is a common edge, or in other words, it crosses the partition, then the value of the terms jij, sigma I, sigma j would be -1. And if it is an edge that lies exclusively in one of the sets, then that term, function term, becomes +1. So now the idea is that we want to maximize the number of common edges, or in other words, we want to maximize the number of edges that have the value of -1, or in other words, numerically, it would be equivalent to minimizing this function that is shown at the bottom right, given by this h. So the idea here is that combinatorial optimization problems can be expressed as the maximization or the minimization of a function, but of course, this maximization takes place in a higher dimensional discrete domain. So since since optimization is essentially a combination, is a maximization / minimization of the function, one simple way to do it would be, on a digital computer, where we create a Boolean abstraction and then run an algorithm that minimizes or maximizes the function. The problem with that is that this has been shown to be NP hard. And so of course, the idea is, can we figure out a better way to create this minimization or maximization process? So one alternate approach could be that we essentially design a physical system whose function, be it energy function or entropy function, can be directly mapped to this combinatorial optimization function. Because if we can do that, then what that would imply is that we would be able to minimize or maximize this function naturally, because the system is naturally going to minimize its energy, and as it evolves towards the ground state, it would naturally minimize that function, or its energy function, and in the process also end up minimizing or maximizing the objective function, depending on how it is mapped to your physical system. And so this idea of essentially allowing the physics of the system to do the computation is something that we have explored in my group. Now, of course, this idea on itself is not unique to us. In fact, it's been explored for the past couple of years, and some of the highlight approaches that have been explored include the famous D-wave quantum annealer, which essentially designs, which essentially uses qubits to create a system whose energy is minimized, and in return, it essentially solves the objective function of the combinatorial optimization problem. Other approaches include optoelectronic oscillators, so building oscillators in the optical domain, and then even other approaches such as CMOS-based annealing, which is trying to create a virtual energy minimization function in memory, for example. In this case, it was SRAM. And then our approach, which is using dynamical systems of oscillators as the hardware substrate, and using the energy function of these coupled oscillators to create an equivalent to the objective function of the optimization problem. Now, of course, all of these approaches have their pros and cons. With quantum annealing, it's considered to be computationally powerful, because it fundamentally aims to reduce the complexity of the problem, although it is quite debated. But the challenges include sub-millikelvin temperatures and enormous amount of power usage to support that kind of cooling requirement. So the D-wave system essentially uses 25 kilowatts of power for cooling the system to sub 1 Kelvin. Optoelectronic oscillators, on the other hand, have the advantage of speed, but scalability is a big issue, because it requires a 1 kilometer long optical fiber that only gets larger as the size of the problem increases. And so, solving really large problems with that is going to be challenging. With the CMOS-based annealing, the advantage is it's compatible with existing process technologies, but the speed up and reconfigurability of the system is rather limited. Now, on the other hand, we in our work have focused on oscillators, specifically dynamical systems of oscillators, for the reason that they are they're a low power solution. Each oscillator in our case consumes about 10 microwatts of power. They're IC technology compatible, and are compatible with room temperature operation as well. The unknowns in this equation, of course, include the eventual scalability to hundreds of millions, hundreds of thousands, or hundreds of millions of nodes, and then eventually looking at the performance at these large nodes as well. So the reason why we have chosen the oscillators is because of the energy efficiency of the system, and particularly in the context of the target applications we want to go after, which is looking at pushing intelligence to the edge, where systems have to operate under energy constrained environments. We believe that this is a particularly attractive solution. Now, with respect to the oscillator system itself, you can essentially tailor the architecture of your oscillator system to map to different objective functions. The optimization, as the optimization problem changes, we are looking at different objective functions, and then the idea is that we can tailor the function of these oscillators to create the right equivalence between the system and the problem. Now, of course, we have specifically looked at two such variations. The first one is that of distance computation in high dimensional space, and the applications of this are essentially for computing degree of match, for image inference in real time, and the other one is the Ising machines, which is the other application, and it's more tailored towards solving combinatorial optimization. Now, of course, the high dimensional distance computation is something that I'll describe in my project pitch, and so I'll not spend time on it here, and I'm also happy to answer questions offline as well. But for this talk, we will essentially focus on the application of oscillators as Ising machines. So it turns out that the Ising model actually has its origins in the domain of physics back in the day, when it was used to describe the domain arrangement in spin glass systems. But over the recent last couple of years, it has been found out that the model can also be used to describe the objective function for many combinatorial optimization problems, including the max cut problem, which we looked at in the earlier slides, as well as other problems like the max clique and the maximum independent set, and so on and so forth. So the idea here is that if we can create an oscillator architecture such that the energy function describing the oscillator system can be directly mapped to this Ising function, then such an oscillator system would be able to compute the spectrum of the large spectrum of combinatorial optimization problems whose objective function is the Ising model. And so it turns out that this can be done relatively easily by creating this topological assignment that's shown on the top right. So every spin in the model, again, this was done for spin glass systems to begin with, so the name has stuck. So every spin is represented by an oscillator, and then the interaction between every spin is represented by a physical coupling element amongst the oscillators. And so it turns out that when you analyze this the system, you can figure out the energy function and prove it to be equivalent to the Ising function. And the corresponding system dynamics are described by the stochastic differential equation that is shown at the bottom right. Now, of course, we at our end are interested in the physical implementation of this oscillator-based Ising machine, and so we essentially built this integrated circuit of 30 oscillators with the ability to couple each oscillator to other in a reconfigurable fashion. So to achieve this, we had to start off with 30 oscillators, and these were Schmidt trigger based relaxation oscillators. And then we had to incorporate about 870 reconfigurable edges or coupling elements to allow this sort of reconfigurable system. And the advantage of this was that we could essentially solve a map with arbitrary edge connectivity amongst the oscillators, giving us the opportunity to look at a broad spectrum of graphs and their properties. Now, the question is, how does the system behave? So here is a representative example. So the graph that we want to solve is shown on the left with the blue nodes and the edges. We then build a corresponding topologically equivalent oscillator system. So oscillator represented by node, and then the coupling edge represented by edge. And then we essentially allow the system to evolve. And what we observe is shown in the time domain data, where you can observe that under second harmonic injection locking, which is the condition required for Ising implementation, we see that the phases of the oscillators form these two partitions. And you can then go on to prove that these two partitions correspond to the two sets that are created by the max cut, or while solving the max cut problem. And in fact, the oscillator phases are, in other words, are doing nothing but solving the max cut problem itself, because the max cut function can be directly mapped to the Ising model. Now, of course, we have done this for many other graphs, as you can see at the bottom left, with different sizes. So we went all the way from 10, 20, and 30 node graphs with different edge densities, and we observed that oscillators compute high quality near optimal solutions. So if you look at the graph on the left, the x-axis shows the optimal solution for the graph we used, and then the y-axis shows the max cut measured using the oscillators, and most of the solutions lie close to the y equal to x line, indicating that the solutions are close to the optimal solutions for the problem. And then the one on the graph on the right essentially denotes the cumulative count of the many graphs that we have solved. Now, of course, that was a prototype demonstration. Going forward, we want to build on this demo and create an even larger system where we expect to see even larger benefits as compared to the smaller 30 oscillator system. So right now we have a 1 kilobyte or 1024 oscillator based Ising machine that is being taped out. And here, of course, won't get into all the details, but we have this FPGA like architecture, which gives us an enormous level of reconfigurability in the system, and we expect to see the real gains in the computational performance with respect to digital algorithms. Now, of course, while this experiment is going on, since we understand the system dynamics, we can obviously create a virtual emulator that allows us to assess, guide, and support the experimental effort. And so here with this, we've gone to much larger graphs, and we've solved graphs all the way up to 50,000 nodes. For example, the Facebook graph, that is the last one in the column, and you can observe that all of these graphs can be solved by the oscillators in less than 90 minutes each. And if you were to solve the same graph on a digital computer using this specific manifold optimization algorithm that we've used at benchmark, we observe that in most cases we are unable to complete the computation. And of course, our timeout criteria here is about 24 hours. So you can observe that it is in all of the cases we see approximately a 10x gain in comparison to the standard digital approach. And remember, this is on on a virtual emulator. So here we are still not using the full potential of the system and using the physical energy minimization to our advantage. And so when we benchmark this system and project the performance to a real physical system, here are some of our estimates where we observe that for a 10,000 node graph, we would be below 1 joule of energy per compute, and we expect this computation to be done in less than a second. So we have another multiple orders of magnitude gain, even in comparison to the virtual implementation that we have looked at as well. And so, in summary, a few takeaway points are that natural energy minimization in dynamical systems provides a useful tool and approach to solve combinatorial optimization. In our case, we've explored coupled oscillator-based dynamical systems to evaluate or implement this approach. And the reason for that is they provide a low power, energy efficient hardware substrate for doing this. Our initial demonstration with 30 oscillators has provided preliminary promising results, and we hope to extend that to larger systems, including a 1 kilobyte oscillator Ising machine. And the early performance of this oscillator-based computing is promising. So with that, I'd like to conclude my presentation, and thank you for your time.